All right, this video is an introduction to trigonometric substitution. And so we actually want to start with a quick algebra review. And so I've got six expressions written on the screen and simplifications of those expressions. And I want to know which of those are correct and which of those are incorrect. And so I'd like you to actually go ahead and just pause the video and think through which of those simplifications have I performed correctly and which ones have I messed up on. And at least one is correct, at least one is incorrect. So pause the video, see if you can figure that out, and then check with me in just a minute. Okay, and so if you're looking at these, definitely this and this are wrong. And so you cannot split addition and subtraction underneath a square root. One quick way to see that is that if you could, the square root of 9 plus 16 would be able to be done by doing the square root of 9, not 3, the square root of 9 plus the square root of 16, which would be 3 plus 4, which is 7. The square root of 9 plus 16 is the square root of 25, which is 5. This has to be correct, so that's incorrect. You can show similarly that you cannot do this for subtraction, but you can't split addition and subtraction. Generally, you can split multiplication and division. And so when we look at the division, that one's actually correct. The square root of x to the fourth is x squared. The square root of 25 is 5, and you're able to take the square roots of those independently. When you look at the bottom two, it's important to note the difference between the square root of 16 and the square root of x to the 16th. So the square root of 16 is obviously 4. The square root of x to the 16th, however, is x to the 8th, because x to the 8th times x to the 8th is x to the 16, because you add powers. X to the 4th times x to the 4th is not x to the 16th, it's x to the 8th, and so that doesn't work. And so the bottom two, obviously only one of those can be correct. The one on the left is correct. The one on the right is incorrect. And so actually the last one I want to talk about is the first example, the square root of 25x squared. That's a little bit questionable depending on the assumption there. So in general, that is incorrect. And the rationale why is that the square root of x squared is not always x. And if we think about why that is, the square root of, say, 25 would be what you would get if you had x equals 5. So like if x is 5, you get 5 squared, which is obviously the square root of 25, which is 5. That is equal to x. So let's write it that way. So square root of x squared is equal to the square root of 5 squared, which is then equal to x. But if x is, say, negative 7, then the square root of x squared is equal to the square root of negative 7 squared, which is the square root of 49, which is 7, and that's not equal to x. In general, you can say that the square root of x squared is equal to the absolute value of x, and so a correction on this would be 5 times the absolute value of x. This is not something we're going to focus a lot on within trig sub. The simplification for the square root of 25x squared is correct if we assume x is positive. So we're going to ignore the absolute value until a later video when we go through the theory for trig sub. But that is something to note, that if we don't know that x is positive, the square root of x squared is not actually x, it's the absolute value of x. The reason it's okay on this x to the 8th and x squared is because we know those answers are positive or 0. So x to the 8th is always greater than or equal to 0. X squared is always greater than or equal to 0. So we don't have to worry about the absolute value. Okay, so two big things here. One is that the square root of x squared is really the absolute value of x. We're going to mostly ignore that when we're first doing these problems. And the second thing, the more important thing, is that you're able to split up in a square root, you're able to split up multiplication and division, but you are not able to split up addition and subtraction. And so this is just a brief overview of that. And this is an important idea when we get to trigonometric substitution. Okay, so what I want to look at is if we have a square root like this. So if I have the square root of, say, 25 minus 16x squared. So based on what we were just saying a few minutes ago, you cannot simplify that directly. So we can't make that 5 minus 4x or 5 plus 4x or any other easy simplification we might think of. What trigonometric substitution ends up being is a method primarily to get rid of square roots within integrals. And so we're going to do something real weird, and I'm going to walk you through this process first, and we just follow what is happening. And so what we're going to do on a trig sub problem is we're going to choose x. And in this case, we're going to choose x to be 5/4 times the sine of theta. And we'll talk in a few minutes about why we would choose that. But if we choose x is 5/4 sine theta, then what happens is we replace the x with that. And so we'll do that in blue so it's clear. But we get 16 times 5/4 sine of theta in place of x, and then we get squared, obviously, and all of this is under the square root. And so we're just replacing x with whatever we chose for x. And so if you simplify that, you get 25 minus 16 times 25 over 16 sine squared theta. The 16s then cancel, so we get 25 minus 25 sine squared theta. The 25s factor out. And because we have 1 minus sine squared is the same as cosine squared based on the Pythagorean identity. So we know that this is 25 cosine squared theta. The reason that this works well is because now somehow subtraction has been changed to multiplication using a substitution and trig identities. We're able to take the square root of each part. And so the square root of 25 is 5. The square root of cosine squared is cosine to the first. We are ignoring the absolute value for now, but in 2 videos, so the video after next, we'll talk about why that part is okay. But aside from that, we should make sure, pause the video until we make sure we understand what is happening on each step. Okay, now I want to do another one before we talk about how to choose these substitutions. So let's say I have the square root of 9x squared minus 36. Let's not do 36. Let's do 49 here. So the square root of 9x squared minus 49. So in this case, we're going to choose for x to equal 7 over 3 secant theta. What that lets us do is it lets us replace the x with 7/3 secant theta. Now if we square those, we get 9 times, or square that, we get 9 times 49 over 9 secant squared theta minus 49. The 9's cancel. So we get secant squared theta minus 1. Because of the identity, 1 plus tangent squared is secant squared. We know also that secant squared theta minus 1 is tangent squared. So we can replace secant squared theta minus 1 with tangent squared theta. That has now changed the subtraction into multiplication. And so we get 7 tangent theta. Again, we're ignoring the absolute value part for now, but aside from that, each of those steps what is happening with each of those steps should make sense given the substitution x equals 7/3 secant theta. Okay, so now what I would like to do is talk about how do we know what this substitution should be. So how did I know to pick 7/3? How did I know to pick secant? And then back up here, we'll separate this with a line. Back up here, how did I know to pick 5/4 and how did I know to pick sine theta? Okay, so we have 2 Pythagorean identities that I've used. So one of them is this 1 plus tangent squared theta equals secant squared theta. And one of them is sine squared theta plus cosine squared theta is 1. Okay, so to pick the trig function, which is actually the trickier part, what I wanted to have happen is I wanted to have a positive trig function squared so that I could take its square root. Normally we wouldn't care if it's positive or negative, but under a square root that matters. And so we wanted a positive trig function squared. Well, manipulating this identity on the top right of the screen, I know that 1 minus sine squared theta can be replaced with positive cosine squared theta. So I knew from the beginning that I was going to end up with 1 minus sine squared theta. The reason I knew that is because the trig function was going to go in place of the x. I was setting the coefficients up so that I could factor out something and get 1 in place of the constant term and then a trig function squared in place of the x term. So on the bottom problem, the way that I knew to pick secant is I knew that the trig function would end up in place of x. I will get 1 in place of the constant term and a trig function in place of the x. I knew then that I could get secant squared theta minus 1, which can be replaced with tangent squared theta. That guaranteed me that I was going to get a positive trig function squared, which would be easy to take the square root. So the idea is, if I have 1 minus x squared, or a constant minus x squared, if I pick sine, then the trig sub will work out. If I have x squared minus a constant, then I pick secant and the trig sub will work out. Also, if I have addition in either order, 1 plus tangent squared can be replaced with secant squared. And so when we do trig substitution, it's typical that we would use sine, secant, or tangent. Subtraction, the order matters. So if we have 1 minus sine squared, we're going to end up with positive cosine squared, but the sine has to be the second thing in the subtraction. When we have secant squared minus 1, the secant has to be the first thing in the subtraction. On addition, the order does not matter, so it could be 1 plus tangent squared or tangent squared plus 1. Anytime we use sine, we could also use cosine. Anytime we use secant, we could also use cosecant. And anytime we use tangent, we could also use cotangent. So what we'll typically use are sine, secant, or tangent because those will work completely fine. And so if we have it in this form, 1 minus sine squared theta, we use sine. If we have it in this form, secant squared theta minus 1, we use secant. And if we have addition in either order, we're going to use tangent. So that's how I knew to pick sine in the first problem. I knew it was going to be 1 minus trig function squared. That's how I knew how to pick secant on the second problem. I knew it would be secant squared minus 1. Okay, how did I pick the coefficient? So I wanted to end up with the same coefficient on both parts of the subtraction. That means that I was able to manipulate the 16 in the first problem. So I knew that I would be able to change the 16 and end up with 25. So I picked 4 on the bottom because the 4 on the bottom would be squared and then cancel the 16. So I picked the 4 to cancel the 16. I picked the 5 to match the 25. On the second problem, I am able to mess with the 9. So I'm able to change the 9 and make it match 49. So I put 3 on the bottom knowing that that would cancel out the 9. I put 7 on the top knowing that that would end up with 49. Okay, so let's look at another problem and see if you can pick the correct trig substitution for this problem. So if I have 16x squared plus 25, see if you can pick the coefficient and the trig function, either sine, secant, or tangent, that you should use for x. So the coefficient and the trig function that you should use for x. Pause the video, write down what you think, and check it with me in just a minute. Okay, so on this problem, you should pick 5 over 4. So the coefficient, we pick that way because the 4 will cancel the 16. The 5 will get me a 25. And then I'm going to end up with a trig function squared plus 1. So I want to do tangent theta because I want to use this form where I have a trig function squared plus 1. Okay, now if you've understood how to pick that, try to do the substitution and the simplification so that you get it down to an answer like 7 tangent theta where there is no square root. Pause the video, try that, and then check it with me in just a minute. Okay, so if I replace x with 5/4 tangent theta, then I get 16 times 5/4 tangent theta squared. Whoops. Square the whole thing. Tangent theta squared plus 25. We square that, so we get 16 times 25 over 16, tangent squared theta plus 25. The 16s cancel, so we get 25 tangent squared theta plus 25 under the square root. We factor the 25 out. One plus tangent squared is secant squared, and the square root of that is 5 secant theta. Okay, once you get the hang of this, the simplification is basically the same every time. You square something, you factor things out, and then typically you take a square root. Trig subproblems normally involve square roots to get rid of, although there are examples where you can use trig sub and not have a square root. But the point of this video is to be good at picking what x would equal and being able to simplify this where there is no square root anymore. So to be able to do this process. So what I'm going to do now is I'm going to put about 3 or 4 more problems on the board and not work them all the way, but I want you to pause the video and come up with what the substitution should be. So what fraction should you choose and which trig function should you choose? So again, as a quick review, because of the Pythagorean identities, we have these 2 that we use over and over again. Sine squared plus cosine squared is 1, and 1 plus tangent squared is secant squared. Manipulating those, we can use for trig sub these patterns. 1 minus sine squared can be replaced with cosine squared theta. Secant squared minus 1 can be replaced with tangent squared theta. And 1 plus tangent squared theta, 1 plus tangent squared theta can be replaced with secant squared theta. For subtraction, the order matters. For addition, the order does not. The forms I've got in blue on the right-hand side of the screen, that's the form of the thing you're using the substitution on. So typically what's under the square root. The 1 will be in most problems, the 1 will be a constant. The sine or secant or tangent will be replacing an x. Okay, so let's put several on here and then let you decide what we should be doing in each case. So 9 plus 49x squared under square root. If we have the square root of 16x squared minus 81. If we have the square root of 36 minus 25x squared. If we have the square root of x squared plus 25, square root of 49 minus x squared, and the square root of 9x squared. So when I said 4 or 5, apparently I meant 7. But try these problems and then check them with me in just a minute. All right, so just come up with a substitution, pause the video, do that, and then check with me in a minute. Okay, so on the first problem, we should pick 3/7. We want to cancel the 49. And we want to end up with 9, and then this is addition, and so we want to use tangent. So we want to end up with 1 plus tangent squared. On the second problem, we want to pick 9 over 4, secant theta. On the third problem, we should pick 6 over 5, sine theta. We know it's going to be 1 minus a trig function squared, which matches that first identity. Here, we don't want to cancel anything. So on the x squared plus 25, we don't want to cancel anything, and we want to end up with 5. So it's important that we end up with 25. So it's important we pick 5 tangent theta because it's addition, 5 because we want to end up with 25. And it's important to make the distinction between 5, which is correct there, and 1/5, which is not. And then here, same rationale, we're going to use 7 sine theta. On the next one, we want to cancel the 9 and end up with 1, and so we use 1/3 instead of 3. We want to use 1/3, and we pick secant theta. And then on the last one, we're going to use 1/4 sine theta. Okay, so this will be kind of the first step in a long line of steps for trigonometric substitution problems, but it is important to be able to identify what trig substitution would make sense. And then in most cases, there's going to be a square root to get rid of. And so making sure you're comfortable going through that simplification is important. We don't have a separate worksheet or anything on this. You'll be doing this within larger problems, but it would be helpful to make sure you're comfortable doing the examples in the video before advancing to the next video. All right, thanks for watching.